ls, and that's going to be the sum over k's and l's, right? Well, oh man, no, the sum over i's and j's, rather. I1 ir, j1 js, all those indices, right? And again, I need a p, I1, oh goodness gracious, wait a minute, I gotta be careful. I really wish I hadn't erased all those things. Can you just tell me what was the formula for like what was my, if we can remember this one, I'll be able to do this. What was my coordinate change for B, lower I, upper J? What was the formula for that? Sum over what, K and L?
Plus B, EI bar, J, upper J bar.
No, I need what's the P's in the?
BI, upper K, K, L, upper J.
Wait a minute, P lower I, upper K?
Yes.
And then Q?
Q, lower L, upper J. B.
Okay, and oh yeah, and then the B,
Lower K.
lower, upper L. All right, so on the basis of that, we can sort out the pattern here, okay? So like, because that is actually a tensor. See, that's a type 1,1 tensor, is what that is. So the bilinear forms that we looked at at the start of today are either type 0, 2, type 1, 1. Oh, they don't fit the pattern, do they?
There's one that is.
Yeah, you see the problem?
Yeah.
So we made a choice here that basically excludes from consideration 2 of my first 4 examples in terms of the nomenclature. Whatever. But, and I seem to have switched the lettering, right? Let me undo that because it's just less, I know my brain, and I'm going to accept my humbling here and just put the letters so that they match up better. All right, now I got my sum over the K's and the L's. And I have a P, I1, upper K1, P, I2, upper K2, P, I, R, upper KR, Q. Lower L1, upper J1, Q, lower L2, upper J2, Q, lower LS, upper JS, and then my tensor in its K1, K, R, and then upper L1, LS. And there you go. That is the coordinate change rule for a type RS tensor. And the mathematics of why that's the case is pretty much what we did at the start in terms of 1,1 tensors. What's really interesting is that when we go to the next chapter, all of a sudden I felt like I didn't have my mic on. I was like, no, I've been doing this whole thing without sound. Dumb. I will do that kind of thing. Anyway, when we move on to chapter 10 and we add calculus to the mix, well, it turns out that the coordinate change matrices actually are like partial derivatives of the new coordinate system in terms of the old, or vice versa. So these all end up being like partial x bar, or partial x bar partial x, and it's even more like elegant, like the way that the coordinate change matrices are related to the bases in terms of the partial differentiation. And we're also able to use, for the basis E1 through EK, we actually use partial derivatives, like partial x1 is like the E1 and so forth. and the dual basis becomes differentials, as we'll see. But that's a forward comment. Now, so this is what an RS tensor is. I want to look at more examples. So let's look at okay. So if we just have like R0, if we have like an R0 or a 0s type tensor, right? If we either have type R0 or 0s, then this would be like tensor on V. This is a tensor on V dual, right? We would actually call them both tensors on V. This language is a little bit flexible. But my larger point is, if all of the entries are from the same thing, then you can then discuss symmetry or anti-symmetry, right? And like so a tensor on V is completely antisymmetric if any interchange of inputs gives you a minus. And it's completely symmetric if any interchange of inputs gives you a no sign change, right? So to properly discuss that, we need to introduce like multi-index notation, all right, which you've seen a little bit of as we've studied the supermath together, right? So it's not totally new to you, but for most students here, it's totally like, what? So in the multi-index notation, I guess, well, oh, you know what I didn't do here yet? Let me write something in the multi-index notation. So I didn't write the formula for t itself, right? Like this is a formula for what t does on this tuple of things, right? But we can also write a formula for t, just like I wrote formulas for b over there, So here, basically this, we think of this as like e I1 acting on x1, and of course this would be like e j1 acting on alpha 1 using the double dual. So you can take all of this and look at it, extending our definition of tensor product to more things. This would be like ei1 tensor ei2 tensor tensor eir tensor e lower j1 e lower j2 tensor tensor e lower js, all of that acting on x1 through xr alpha 1 alpha s. And then you can pull that out, right? You can pull that out, and then you find, of course, that we can write t as the sum over, let's say, I and j of t, well, lower I, upper j of e I tensor e upper j, like that. If I can use that brief notation. And of course, what I mean by this is this much more insidious I1 IR J1 JS T I1 IR J1 JS EI1 tensor tensor E IR tensor E upper J1 tensor tensor E upper JS. But there you go. That's how we can either using the multi-index notation or just using the plain, expanded out in gory detail component notation, we can build a tensor, an arbitrary tensor, from the tensor product of vectors and their dual vectors. Okay, that's what's going on there. And so what does that say about the dimension of the set of type RS tensors? Like what's the dimension of it? How many is a vector space? Is it a vector space? Question, like is this a vector space? You think about it, search your heart, you realize it is. If I add two tensors, it's going to be a tensor again, right? Because the usual definition of function addition, plays nice with this linearity in each slot. And what else? Well, okay. And then if you just look at this, you can prove that for the arbitrary type RS tensors that the set of all such things forms a basis. This formula right here shows you spanning. And then linear independence of this tensor basis can be proved by arguments similar to the ones we gave last time. You simply let this act on an appropriate tuple of the basis and the dual basis, which gives you Kronecker deltas galore, which then forces the components to be zero in the linear combination, so just like we did last time. So in fact, that is a basis for the type RS tensors, which shows you that a type RS tensor, the set of all type RS tensors, has dimension of, I guess it's dimension of v to the RS power. So like if you had a trilinear tensor on a two-dimensional vector space, the set of all trilinear maps on a two-dimensional vector space would be 8-dimensional, because 2 to the third is 8. If you look at all of the bilinear maps on a two-dimensional space, well then that's 4-dimensional, because basically it's governed by a 2x2 matrix. For a trilinear map, it's kind of like a 2x2 cube, because like a trilinear map, if you look at the formula, it looks something like if we have t of x, y, z, we've got sum over ijk, right? X upper I, y upper j, z upper k, and then t, ijk, right? I guess this is my example, question mark. I don't know what example this is. 10. It feels like example 10. So, all right, so that would be, I mean, it's an interesting thing to start thinking about, like, what is, I mean, I remember as an undergraduate, I was like, well, what is a tensor? What is it? If it's got 3 indices, what does that make it? Because 2 indices is a matrix, what's 3 indices? Well, I mean, if you want to envision the set of indices in some sort of geometric object, then you could think of it as a cube of components if you wanted. But I don't know how useful these kinds of thoughts are. Like, what about when I've got like type 2-2? I've got 4 indices. Like, how do I visualize that? I just don't visualize it, okay? I don't think visualizing the set of tensor components as a geometric object is particularly useful. Now, here's where it could be useful. It could be useful in as much as you're trying to take a sum over 3 indices and break it up into distinct, like a partition to distinct categories, kind of like I did down here. See, that's a picture of 2 indices, and I like that. So there could be something like that could be possibly useful in terms of like representation theory or something. But that would be a trilinear map. This would be a type what? In terms of our notation, that's a type what tensor? Type 3,0 tensor. And we could say on R3 if we wanted. It really depends on where x, y, and z are from, right? Here's a specific example of a tensor. How about this? We could say t of x, y, z. Well, let's do x1, x1, x2, xn. We can do determinant of x1, x2, xn. All right? That is actually a tensor. The determinant is an n-linear map. Because it's, I don't know if you know this or not, but the determinant is linear in each column. So this is a n-linear map. There's actually a formula for it. I don't know if you know this or not. Have I told you about this before? That is my definition for the determinant in linear algebra. Where here, this is the so-called Levi-Civita symbol. And it goes like this, 1, 2, n is equal to 1. And then the rest of the values are under the assumption it's completely anti-symmetric. So like, for example, epsilon 2, 1, n is minus 1. If any index is repeated, it's 0. So this is the so-called Levi-Civita symbol. Sometimes it's called the completely anti-symmetric symbol, but that's what the Laplace expansion by minors puts into practice. Now there's a considerable distance between that formula and Laplace's expansion by minors that we teach in linear algebra, right? The thing where you do the subdeterminants and expand. Like proving that that formula is the same as Laplace's expansion by minors is not an entirely trivial problem. But it can be done. It's in my linear notes. At least some attempt at it is in my linear. I'm not sure it's really in my linear notes. If you want to be more critical, probably can't stop you. But the determinant is a tensor. It is a real valued tensor. It's an n-linear map. It's a multilinear map. It's probably the most important multilinear map, honestly. And in future lectures, we're going to explore. I'm going to tell you first of all. So next time, we will do our homework. Well, I don't know if it's homework, but we will do our due diligence, and we'll talk about permutations, and we'll talk about how to define complete symmetry and complete antisymmetry for a tensor, either on V or V dual. We'll just say on V. Because if we define it on V, we can just replace V with V dual. We've got it, okay? It's the same definition. We'll define completely symmetric and a completely antisymmetric tensor. And I'll define it in terms of permutations, and then we'll build the wedge product of vectors. We'll show how any antisymmetric tensor can be expanded as a wedge product of dual vectors, and it's just going to be from the complete antisymmetrization of the tensor product. That's all that this was. This is the complete antisymmetrization of 2. If you've got 3, then you just do the sum of all symmetric permutations and the sum of all, anyway, you just have to look at the sign of the permutation of the indices you start with versus what you write. So it's an inherently combinatorial problem. There's no nice clean-cut formula that doesn't involve permutations. So it is what it is. Which is also the power of the wedge product, because it folds all of these combinatorial ideas into the simple concept of the wedge product being distributive, associative. It's an associative product. That's amazing, because the cross product is not. And so while the wedge product is like the cross product, it's not the cross product. it's much better than the cross product, because the wedge product is something we can take of arbitrarily many vectors. It's, you know, I would say it's endless, but if we're in an n-dimensional vector space, we'll of course learn, as you pointed out, that, you know, it's essentially the super numbers. It's the Grassmann algebra, the exterior algebra altogether. If we look at the direct sum of all the different kinds of wedge products you can form. So that's what we're getting into like Thursday, probably. So anyway, man, I sure hope people come to Complex today with I know football is people's first love. So I hope I'm not talking to myself. I don't know.